In this video, we will do three things. First, we will understand how quicksort works with Lomuto partition, step by step from start to end using a full example. Then we will look at the Python code implementation, and finally, we'll break down the time and the space complexity. But before we look at the algorithm in action, let's understand how quicksort works. To sort a list of numbers using Lomuto's partition scheme in quicksort, here's what we do. We pick the last element as the pivot. Pivot is the element we use to divide the list into two parts. Next, we compare the rest of the numbers with the pivot and rearrange them in such a way that all the numbers smaller than the pivot are on one side and all the numbers larger than the pivot are on the other side. Then we place the pivot between these two sides. At this point, our pivot will be at the correct final position in the sorted list. After this, we apply the same steps recursively on the left side and the right side of the pivot. We keep doing this recursively until the entire list is sorted. Now let me explain to you how we will rearrange the elements around the pivot. We start by initializing two variables I and j. I marks the boundary between the elements smaller than the pivot and the rest. Think of it as the wall that separates smaller elements from the bigger ones. We initialize it to one position before the start of the subarray being sorted. J is the iterator. It moves through the list, starting from the first element and going up to the element just before the pivot. As we move j through the list, whenever we find an element smaller than the pivot, we move I forward by one step and swap the elements at the I and the jth position. After j has scanned the entire list, we swap the pivot with the element right after I, placing it exactly between the smaller and the larger elements. You will understand it in much better way once you see algorithm in action. So let's get started. Our goal is to sort this array using quicksort with the Lomuto partition. We start by initializing I at -1, which is one position less than the lowest index. Then we initialize j at the lowest index, which is 0. So j points to the first element 7. The pivot is the last element of the list, which is 5. Now we start iterating through the list with j moving from index 0 up to index 7. We compare the element at j with the pivot is 7 less than 5. As that's not the case, we do nothing and move j forward. Next, we compare 2 with 5 is 2 less than 5. Since it is, we increment I by 1 and swap the elements at the ith and the jth positions. So swapping 7 with 2, then moving j forward. We then compare 4 with 5. Is 4 less than 5? Yes, it is. So we increment I by 1 and swap the elements at the ith and the jth positions, swapping 7 with 4, then moving j forward. We check if 9 is less than 5. Since it's not, we just move j forward. We compare 3 with 5. Is 3 less than 5? Yes, it is. So we increment I by 1, swap elements at the ith and the jth positions. So swapping 7 with 3, then moving j1 forward. Next, we compare 1 with 5. Is 1 less than 5? Yes, it is. Again, moving I forward and swapping 9 with 1, then moving j forward. We then check if 8 is less than 5. Since it's not, we just move j forward. And then we check if 6 is less than 5. Since it's not, j has done iterating. So now we swap the pivot with the element at the I plus 1th position. So swapping 7 with 5. Pivot 5 is now at index 4, which is its correct sorted position. And as you can see, all the elements to the left of the pivot are less than it, and all the elements to the right of the pivot are larger than it. We now recursively sort the left and the right sides of the pivot. Let's continue with the left side. Again, we choose the last element as the pivot, so 1 is the pivot this time. Then I is at one position before the first element and j is at the first element. We check if 2 is less than 1. Since it's not, we just move j forward. Then we check if 4 is less than 1. Since it's not, we just move j forward. And finally, we will check if 3 is less than 1. Since it is not, j has done iterating, so we swap the pivot with the element at the I plus 1th position. So swapping 1 and 2. Pivot 1 is now at its correct position. Before we look at the code implementation, let's enjoy watching the rest of the algorithm in action. Here is the Python code implementation, and as you can see, we have two functions, quicksort and Lomuto partition. Low is the starting index and high is the ending index of the subarray we are sorting. Quicksort calls Lomuto partition, which picks the last element as the pivot. I marks the boundary of the smaller elements starting at low -1. J goes from low to high -1, and whenever we find an element smaller than the pivot, we move J forward and swap the elements at the ith and the jth positions. Finally, we swap the pivot with the element at the I plus 1th position, placing it in its correct sorted position. Quicksort then recursively sorts the left and the right subarrays, and then the entire list is sorted. Let's do the complexity analysis for the Lomuto partition quicksort. The best case time complexity of quicksort will be O(n) of log n. It happens when pivot splits the array into two almost equal halves each time. The reason why it is O(n) of log n is because at each partition step we scan n elements. Splitting evenly gives us about log n levels of recursion, and multiplying these together gives us O(n) of log n. The average case time complexity of quicksort will be O(n) of log n as well. It happens when the pivot splits array reasonably well, not perfect but not highly unbalanced, so around 40 to 60%. The reason why it is O of n log n is because we will still have around log n levels of recursion. Each level requires scanning all the element once, so O(n) per level, so total will be O(n) of log n. The worst case time complexity of quicksort will be O of n squared. It happens when pivot ends up as the smallest or the largest element, causing extremely unbalanced splits. Example would be if an array is already sorted in the ascending order and we always pick the last element as the pivot. So the first partition takes O(n), second partition takes O(n minus 1, then O(n minus 2, down to O of 1. Sum of all this will be O of n squared. Now coming down to the space complexity, the best and the average case space complexity of quicksort will be O of log n, because balanced splits mean recursion depth is about log n. The worst case space complexity of quicksort will be O of n, because unbalanced splits mean recursion depth equal to total of n because of the chain of recursive calls. One important note is if we ignore the recursion stack space, the space complexity of quicksort will be O of 1, as it's an in-place sorting algorithm. It only uses few extra variables. Thanks for watching. Please like this video if you enjoyed it and subscribe for more videos like this.